Okay, so the present is of course unknowable and the future is yet to be known. That's in our forward light cone. We only see the past light cone. And we also have some information along our past world line. That's things like if I dig up a rock and measure its age through radioactive dating, and I determine that the Earth is 4.5 billion years old, that's an example of information along our past world line, which is of relevance to cosmology. But most of it actually comes along our past light cone. And you can see that if I am on another galaxy here, I'll have a similar light cone there, I'll have a similar light cone here. And I have no idea whether that person sitting on that galaxy is seeing the same thing along their past light cone as we are. Right? All I can do is to look back along this. At some point it will intersect a constant time surface. That will be the last scattering surface of the cosmic microwave background. And I have to infer everything that I can about the universe from this limited set of information. Right? So it is in this sense that cosmology is not, this is a plot from a talk by George Ellis, a distinguished relativist from South Africa, and he just makes the point that there are fundamental limits to what we can know about the universe precisely because of this restriction, which is just a physical restriction. It is not a fundamental one. In principle, you could imagine, taking a rocket ship all the way across the universe and making the same observation. And in some sense, in cosmology, we are now learning to do that. We cannot ourselves go there, but we can use objects like clusters of galaxies at a redshift of 1, and we can infer from something we can measure from here about what they are seeing of the universe from where they are. For example, from the X-rays that they emit. But that's a much more subtle point. Normally, we are restricted to this. So most of our information, as I keep saying, is restricted to 2 dimensions. We actually see a flat sky, and we have usually no depth information, because depth information is much more expensive to determine observationally. Mapping the sky is relatively straightforward. So here is a map of the sky made by the Sloan Digital Sky Survey, which is still operating. And basically, each of these points here is a galaxy. Okay, there are several million galaxies on this little plot here. Actually, the color coding is meant to reflect the intensity of the galaxy emission in that particular band in which this measurement has been made. But Hubble, in fact, made a very important observation. In fact, what is technically actually Hubble's law, which is that if I have an uniform distribution of sources in a volume, so we have a version of this Olbers paradox that was mentioned, which is that the number of sources in a volume goes as the cube of the scale, and the flux of each source is falling as the square of the scale, right? So the number of sources brighter than some value s will go as s to the minus 3/2. Okay, and this is actually a version of Olbers paradox, because this, of course, will grow in an infinite universe without limit. Now, this is simply coming from the dimensionality. If I have 3 dimensions in which the sources are spread, but 2 dimensions in which the light itself spreads, then I'll have this exponent, right? Now, astronomers don't actually use the absolute amount of light, which will be something like ergs per centimeter square per second per steradian or whatever. They normally convert into something called a magnitude, which is a logarithmic measure. So magnitude m is the log of this brightness referred to some fiducial value, right? And then to confuse the rest of us, they multiply it by minus 2.5. What that does is to make the number bigger the fainter the object is. So remember, the 25 magnitude is a lot fainter than 20 magnitude. Okay, thank you. So what you do is you can ask the question, you see these things on a flat sky, but I can measure their brightness and I can convert it into a magnitude and I can do these counting tests. So let us see what happens when I do this counting test on the Sloan Digital Sky Survey sky map. And I see here is the log of the number of objects per steradian per magnitude, per degree square, sorry, per interval of magnitude. And this is the magnitude. Remember, this is log scale. Okay, although it's shown as linear here, this is a logarithmic measure of the brightness. And I see a line here, and that line is in fact the line that tells us that these objects, which are in fact galaxies, are distributed homogeneously in the volume that is being surveyed. Okay. But there is another line there which you see marked by crosses. Okay. This has a slope of only -1. And in fact, from just studying this two-dimensional plot and making this analysis, I can tell which are the objects which are in our galaxy and which are the objects which are outside our galaxy. Now, can anyone tell me why the slope of stars should be -1 rather than -3/2? I've already given you a clue. It's up here, see? I said that the number of objects goes as the cube, that is that 3 there, and whereas the flux is decreasing as 1/r², so that is the 2, right? But the stars in our galaxy are not distributed in 3 dimensions. They're in a disk, right? So the number of objects is also going as r². And therefore, the number that is brighter than the value s is going as s to the -2/2, which is this line here. You see the power of this method. It actually can convert the information from a 2-dimensional sheet into some 3-dimensional information. And this is very interesting because astronomers routinely try to figure out what they are seeing on the sky. And here is an example of how you do this whenever you discover a new class of source and you wonder what these things are. You do this so-called log n log s test. Sometimes they call it a Vmax Vmin test, but it's the same thing. So, okay, so this is a picture of gamma ray bursts. These are things on the sky that emit gamma rays in a brief flash and then disappear. Okay, and when they were first discovered, people were very. This was some 25 years ago. People were very curious to know what the hell these things were, and so they launched a satellite, and on that one there was the gamma ray monitor called BATSE, and it just mapped all the gamma ray bursts on the sky. And again, the color coding tells you which one was brighter, which one was fainter. But from this map, you can't tell where these gamma ray bursts are. They could be in our solar system. Okay, they could be around the Earth, uniformly distributed, very close to us. But when you do this log n log s test with that same catalog, you see that the number of sources is falling exactly as you expect with this -3/2 source, which is this dashed line, over a finite range, right? But there is a cutoff. When the flux gets very bright, okay, there are fluctuations here which are quite large, and at the faint end, they are departing from -3/2, right? So the deviation from the -3/2 expectation at the faint end is because at that point, the assumption that we are in Euclidean space is breaking down. Okay. Remember that the assumption that the number is going as cube depends on space being Euclidean, and that need not necessarily be so when we look on large scales in cosmology. We'll construct a metric in the next lecture to understand how that works. But for the cognoscenti here, the fluctuations at the large scale, at the very bright flux, might be because there is a source accidentally very close to us, okay, and that is especially bright, and that will peak above the distribution, or you might have a deficit of sources. You might be in a local hole in an otherwise uniform distribution. So you start seeing the fluctuations in the distribution, and you can actually learn a lot just from the fluctuations, as we have learned from the condensed matter people who are very expert on that. However, the complication in cosmology, which you don't have in the laboratory, is that these objects are not standard. All electrons are the same, right? All atoms of cesium are the same, but all galaxies are not the same. They change in time. Now, the first thing is that when we look back at distant galaxies, we are, of course, looking back in time, right? And therefore, we're seeing them as they are when they were younger. And when they were younger, the stars that they had were typically hotter, and therefore emit in the blue part of the spectrum more than in the red part. So there is a evolution simply because you're looking back in time. And then there is the additional complication that galaxies cannibalize each other to make the world of galaxies that we see today. These galaxies are not the same ones that we started out with. There were far more of them, and they merged together, they devoured each other, they grew to become different objects. And that evolution is a complicated story which people are in fact researching today with the best telescopes that we have. But what that means is that the number of objects is not necessarily conserved as you would like to have it in order to have a fiducial in time. And this introduces a lot of complications in cosmology and in observation, which we'll see in detail in the next lecture in cosmology. Now, come back to the question I started out with. How do we construct a mathematical model of the universe? Well, that is simple if you are Albert Einstein, because he has intuition. So he actually didn't have any data, right? Without any data, he just assumed that the universe is homogeneous and isotropic and averaged over large scales, because he wanted to construct a cosmology from the newly invented general theory of relativity, which he had formulated. If he had had access to data, I think he might have been more, how shall I say, hesitant in asserting that, because when you look at redshift surveys, so this is now showing another survey called the 2-degree field survey. This was done from the Anglo-Australian telescope in Australia. And that is showing, again, a picture similar to the Sloan survey, which this predates, the galaxies as a function of the distance. So that's the red shift, the amount by which the wavelength is shifted towards the red fractionally. And that corresponds in terms of distance to this scale which is shown here. And you can see these great tracery filaments of galaxies, huge voids, this so-called great wall, which is come to be called the cosmic web. And in fact, if you stare at that, it is actually obvious that on the largest scales that have been probed, this one has probed out to about 600 megaparsecs, you actually see structure on the biggest scales that you have actually probed. And that makes you wonder, could there be even bigger structure if I probe on even bigger scales? Okay? Has the distribution truly become homogeneous? In fact, when you study the structure on small scales, it is not homogeneous at all. It is fractal. It has a dimensionality of 2, as you will see in data very soon. But the statement that is always made in cosmology textbooks is that if you average it over scales bigger than 100 megaparsecs, which is about this distance here, okay, this much, then it becomes homogeneous. This is the statement that people start with, and then they immediately construct the Friedmann-Robertson-Walker metric and get going. I'm not going to do that. I'm trying to show you some of what the current research in cosmology is about, which is going back to these foundations and asking whether they are really absolutely correct or need modification, because therein may lie a tale and an insight into what we are inferring from the standard model today, things like dark energy. So I think you will agree with me, if you study that plot, that it is not actually obvious that we have a transition to homogeneity on the large scales. We would need to do some analysis on plots such as this to try to understand what the distribution of galaxies actually is. So that you can do even without having the depth information. That what I just showed you was galaxies whose redshifts had been determined, and therefore you know their distance roughly. But most maps do not actually have the depth information. This is the so-called automated plate measuring galaxy survey, also done by the Anglo-Australian telescope, and the 2-degree field was a little field over there. Okay, this is a much bigger part of the sky. It's got about 5-6 million galaxies. And what you can do on this is a test for whether the distribution is actually homogeneous in the same way that we did that log n log s test on stars in our galaxy. If the distribution is homogeneous, right, and of course there are fluctuations on small scales, some extra clustering here, some underdensity there, and so on, then supposing the typical correlation length of these galaxies is some ruler like this, then if I take this ruler further back from you, it subtends a smaller and smaller angle at your position, right? So therefore, the characteristic clustering, the angular scale of clustering of the galaxies on this map should get smaller and smaller as we look at fainter and fainter galaxies, right? Let us assume for simplicity that they're all the same brightness. So the apparent magnitude is just telling you how far away they are, and the angular clustering of such galaxies should be smaller in angle than that of brighter galaxies, right? So this is the angular correlation function of those galaxies, W theta. W theta is simply the excess probability over random of finding two galaxies within a distance theta of each other. Here is theta plotted in radians. So you see that on large scales, which is large angular separations, the correlation between the galaxies is very, very small. It's less than 10 to the minus 3. They're basically randomly spread on the sky. But as I go to smaller and smaller angles, the correlation function is increasing, and at very small angles, there is a larger than average chance of finding two galaxies within a given angle of each other. Also, when I do this exercise using galaxies in different magnitude slices, so here are some bright galaxies, there are some fainter galaxies, more fainter galaxies, right? And those curves are displaced from each other, right? But if I allow for the fact that if I assume that these galaxies are randomly distributed in space and homogeneous as well, then I can expect that this angular scaling function, which is the excess probability of two galaxies within an angle theta of each other over random, that should scale with the depth of the survey, with the distance that I am looking at. And you can actually work this out just from dimensional grounds, that I've got only two scales in the problem. One is the intrinsic clustering scale of the galaxies, that we call that R sub 0, and the other is the depth of the survey, and the only dimensionless quantity I can construct from them is the ratio, right? So therefore, the angular correlation function should just scale with that ratio. If I do that, then I find that these things actually then fall on top of each other. So in other words, if I assume the answer, something that I'm actually trying to see if this data is consistent with, which is that the galaxies are distributed homogeneously, then I would expect the angular correlation function to scale as follows. And when I do that test on the real sky, I find that in fact it is true that the angular scale of clustering of the faint galaxies is actually larger than that of the bright galaxies. But if I do this scaling, then they all come on top of each other, suggesting that my initial assumption was actually not far off, right? Now, there is of course a great deal more information in this plot. For example, this change in slope, why all that is happening, and we'll see how that comes about in a second. So, if it was a truly fractal distribution, then there is no scale in the problem, and then the angular clustering should not change with the depth at all. So therefore, although it is fractal on some scale, it must be the case that it is not fractal on all scales. Okay. Sorry if this is getting a little technical. I'm trying to intrigue you enough that you will follow this up yourself with your own study, right? But maybe these are things that you have not been exposed to before, and I'm just trying to tell you that rather than just start with the standard FRW metric, we should take a moment to look at the actual data on the universe and try to see what you can infer from that. Okay, so let me just go into this in a little more detail so that you understand what the point of it is. So supposing the distribution of galaxies is homogeneous with an average density of n, let me take two volume elements, V1 and V2, dV1 and dV2, and ask what is the probability of my finding a galaxy in volume dV2 if I've got 1 in dV1. So that will be just n squared times dV1, dV2 if they are distributed randomly. But in principle, they could have some additional clustering on top of that, and that I write as 1 plus some zeta. Okay, and that quantity is called the two-point correlation function. Okay, so this is one model of inhomogeneity, that you have some uniform distribution on very large scales, and on some smaller scales you have some excess clustering on top of the uniformity, and that is this autocorrelation function, right? This is what is routinely used in cosmology. It turns out that this correlation function actually falls as a power law, and there is a lot of information in that, but that we are not going to discuss right now. It just means that as I go to larger and larger separations, if I pick one galaxy and ask what is the excess probability over average of finding another galaxy here, 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 that will tend, slowly it will go down and then become constant as I go average over larger scales. It is becoming uniform, right? So this is getting harder to measure. So you can measure something called the conditional density, which is easier. You just pick a galaxy, as it says here, and then you just count the number of galaxies contained in a radius, a sphere of radius r, and then you distribute it by divide it by the volume, and then you get this conditional density, and you can work out. It's a simple exercise. Sorry, can you all see from the back the screen? Yeah. Anyway, sorry, it's on the left hand side. It will be in the slides. The correlation function is related to the conditional density, and the average density of galaxies are so. It's a simple exercise to work that out. So you can measure these things.
The estimator of the correlation function. Right?
Exactly.
So it's the autocorrelation of the
Precisely, but it's a more robust estimator, because measuring this thing, something that is going towards zero, is very hard to measure. Okay, because Poisson fluctuations will become larger and larger. Right. So this is just but mathematically it's the same thing, as you say. However, people who do condensed matter physics say this is really assuming the answer. They say you're trying to prove that on very large scales you can quantify the distribution by just one number, the average number per unit volume, n. But that is what you're supposed to be proving. How can you assume it to start with? Okay. So what they are saying, you should not make any prior. After all, the distribution may not be this model. The distribution may be like a glass, which is another possible distribution, which does not have this property. Okay. So you don't know that. So what they say is, do the same test. You know, pick a galaxy, draw a sphere around it, count how many galaxies are there, make the sphere twice as large, see how many galaxies are there. Of course, if you are in a uniform distribution, the number should scale as r cube, right? Is it really scaling as r cube? So you actually can define in general a scaling exponent that depends on the fractal dimension of the system. This dimension may be less than 3. So for example, if all the galaxies are distributed on a sheet, then the scaling dimension will be 2. In general, it could be something between 2 and 3 if that sheet is intricately folded. Right? So you can imagine that there is a lot of possible complexity in the universe, in principle, apart from this simple model that we started out with of a homogeneous distribution. And the correlation dimension is actually related to this 2-point correlation function according to this formula, which again I invite you to try to derive these things. I'm not going to do it because the only way you are actually going to get a feel for these things is by doing these simple exercises, and then you'll get a sense of where this is coming from. Okay. Of course, these things are in textbooks. You can look up the textbooks. There's nothing wrong with that. But something that we are sure of is that once we get to homogeneity, the number count should go as r cube. Okay. So let us do the test. Now we have got all this data. People have made these massive surveys at great expense over many years. Taken, you know, thousands and thousands of person-years to build these maps. So here is the Sloan Digital Sky Survey, and this particular strip of it has got 4,000 galaxies. Now these are so-called luminous red galaxies. These are visible up to a redshift of about z of 0.5. They're very, very bright, usually the central elliptical galaxy in a cluster, and they are extremely bright. So you can observe them to, so this one is over the redshift range 0.2 to 0.4. So these occupy a huge volume. They're occupying a volume of a couple of gigaparsec cube, right? And again, the color coding here tells you how bright these guys are, right? Now, this survey, the reason why it looks like that on the sky is because it's like a fan, okay? These things are not necessarily three-dimensional. You have to point the telescope, which has got a tiny field of view, and you have to make a map, then you move the telescope and you make another map, and you patch them together. And therefore, you create a patch like this and all these isolated regions. Maybe here you could not look for some reason. There was too much extinction, whatever, in the intervening space. So these surveys of galaxies are not really ideal. They are not as good as we would like. If you wanted to make a simple measurement, we should be, give me an ideal telescope, map the whole sky 4 pi. That simply isn't there. There are just too many galaxies. There are 10 to the 11, I told you, right? But so far, we have really mapped only about 2 or 3 million galaxies in redshift of the order of 10, 20 million just photometrically. So these surveys are not really very, very suited. You can imagine that if I try to draw a sphere in there, I can, of course, draw a sphere which is up to the size of this, the width of this wedge. But if the sphere gets any bigger, then it will pop out of the survey volume, right? So it is not very good to do it like that. And you might be amused to know that some tests which were carried out early on did not put in a check in the algorithm to make sure that the sphere was staying in the volume, and they went wrong because of not doing that properly. Now here is the result of the test, which was only done, you can see here, about 12 years ago. So, you know, all the things I'm talking about are relatively recent realizations in the history of cosmology. So here is the number of those galaxies in a volume of radius r. This is the log of r. So this is 10 megaparsec, This is 100 megaparsecs, right? This is meant to be the scale of homogeneity. And what they're doing here is they take the counts and they divide it by the expected number from a homogeneous random catalog, right? So the reason you do this is because you subject both catalogs to the same constraints on the seeing function, the telescope parameters, whatever. So the two are treated in exactly the same way. So when you take the ratio, all the systematics cancel out. That's the idea, right? And therefore you see that on scales up to about, this is about 50 megaparsecs, the distribution of galaxies is not, if it was going as r cube, then it should be a horizontal line, because the random distribution is going as r cube by construction. It is actually going as 1 power less. It is going as r square. Okay? And that is the fact that I mentioned to you earlier, that the distribution of galaxies is actually fractal up to about 50 megaparsecs, as you can quantitatively see from this plot. But above that, it seems to be tending towards homogeneity. But at this point, you're running out of data. You can't get a box, a sphere big enough into that volume. Also, you notice that they have not shown any error bars here. Okay? What they've done is taken 4 patches of the sky, and these are the 4 patches, okay? And they have done the test separately for all of them, and there is a spread between the lines, which is, they say, indicative of the, uncertainty in the matter. Right? So you technically use something called a jackknife uncertainty to try to quantify this. But this is perhaps not the best way to do it, and if you want to know more, you could have a look at that paper by Franco Siloslavini. He criticizes it from the point of view of a condensed matter theorist. But here we now fast forward to 5 years ago, and there was a survey in Australia called WiggleZ, and they in fact did the same test, and now they are showing that apparently even with including error bars and so forth of the galaxy counts in different redshift slices, right? This is now going up to redshift of 0.9 all the way from 0.1, that in all cases the fractal dimension is going from 2 to 3 as you go towards the larger scales, and apparently already at the scale of 80 megaparsecs we are tending to homogeneity, right? That's what these guys claim. Right? This is often quoted as evidence that the assumption that we make that the universe is homogeneous on scales larger than 100 megaparsecs is definitely true. However, if you look at the distribution of galaxies in WiggleZ and the survey volume, it's not even as good as Sloan Digital Sky Survey. It's extremely convoluted in redshift space. So in fact, the biggest spheres are not fully contained. So if you read through that paper in Monthly Notices, you would find that on about 20 pages in, they've actually commented that yes, we realize that our spheres are not being fully contained. So in fact, we filled the bits that went out of our survey volume with numbers drawn from a random distribution. Okay? But that, of course, is the answer that you are trying to prove. If you fill your galaxies from a random distribution, you are going to infer 3 by construction. So I don't think that the answer that they got is correct. Okay? It is biasing your result in a subtle way towards the value that you are trying to in fact infer from the data. It is not an independent test, right? And so here is an idea. If you want to do some experimental work in this subject, find a proper survey of galaxies and do this study of the fractal distribution and how it tends towards homogeneity. You can perhaps bring to bear much more sophisticated statistical measures. There are Minkowski functionals, there are all kinds of distributions that can be used to characterize this transition. Okay? So the bottom line is that this is a bit dodgy. I would not agree with the results of this survey. And if they were right, there should be no coherent structures in the universe much bigger than 100 megaparsecs. But in fact, people keep finding structures in the universe that are a lot bigger than 100 megaparsecs. So here is an example of a structure that is extending over. So the linkage scale is 100 megaparsecs. So this is extending over something like 600-700 megaparsecs. Okay, this is something that was found in the distribution of quasars in another survey, right? And these people got very excited because it seemed to suggest that there is definitely a breakdown of homogeneity on such large scales. But you have to be a bit careful, because even the distribution of galaxies in the sky need not be random. According to the theory of this CDM, cold dark matter cosmology, there are correlations on large scales which were imprinted due to the initial fluctuations which we believe were from inflation, which actually were the seeds for their formation, for their growth through gravitational instability. And this can induce correlations which you can only study typically by doing numerical simulations of the growth of structure, or if you have the mathematical tools necessary to do it, you can do it by other means. But in fact, when you do that, you find that occasionally, with a few percent probability, you can get large, extended, apparently coherent structures even on scales where you expect that it should be random. Okay. And in fact, Nadathoot did argue that you could get something like that arising by chance. Now the point is that that chance might be a very small number. It might be something like 0.1%. But 0.1% is not a big deal. It's like 3 sigma. Okay, so some fluctuations like that happen all the time when you do laboratory experiments, right? So it is not the case that if you just happen to see it in one survey, that necessarily demolishes the underlying theory. You have to ask whether it is what you have found is unlikely at the level, at least in particle physics, we stick to 5 sigma. So you would really have to ask for a much stricter criterion. It should not be there at the level of something like 10 to the minus 3%. Then we believe it. Okay. Now, some of you who are not used to this might think, isn't that being rather too conservative? I mean, surely less than 1% chance is already, pretty restrictive. But in fact, any particle physicist, especially one who does experiment, will tell you that they see fluctuations like that all the time. In fact, it's a joke in the community that 3 sigma fluctuations happen about half the time. Okay, that although mathematically speaking it's a Gaussian distribution, it should happen less than 1%, but in practice there are always selection effects. So that is something that the mathematical formula does not capture. So just to show you that this is all accessible to all of you, I actually set a undergraduate student I had in Oxford, Avilash Mishra. He's now doing a PhD in Caltech. The task of taking a new data release from the Sloan Digital Sky Survey and doing this test on it. And in fact, the Sloan Digital Sky Survey, the first thing you find is that if you plot the distribution of the galaxies in redshift, it's a very irregular thing like that. Okay, so this is called the selection function. And what this is telling you is that that big sample of galaxies is quite unsuitable for doing any test at all, because it has already got some intrinsic scales. For example, there seems to be a larger than average probability of finding galaxies at that particular redshift. If you are trying to find an inherent length scale in a distribution, try to find first of all, select data that does not already have some scale imprinted on it. Okay, and so you have to cut on that. You have to take out all the faint galaxies and brighter ones, and by the time you get down to galaxies that have a flat selection function, you have thrown away about 80% of the galaxies. So your numbers have decreased. So your Poisson fluctuations have gone up. So you get some flavor of the kind of problems in this game. Okay, but when you do it with that, he claimed that he could. So this is the number of galaxies, which should then divided by the number from a random distribution. So it should go to a dimension of 3, okay? And this is what we get with the test sample, right? We do get 3, but with the actual galaxies, we don't quite get to 3. So this deserves further investigation. And it's kind of funny that only about 3 or 4 papers have been written about this. And given the huge amount of literature in cosmology, this is something that's worth looking at, right? By the way, this is 150 megaparsecs is the scale of the so-called baryon acoustic oscillation peak, which is a measurement of a 2-point fluctuation in the 2-point correlation. But a 2-point correlation only makes sense if you have already reached homogeneity. Okay, so this is the kind of thing that gives me some cause for concern about whether we are really measuring the right thing when you measure on those scales. So let me get on. Sorry, I'm going slower than I would normally go, but hopefully some of this, please tell me if I'm going too fast, okay? Do interrupt. Right. Let me come to something which is direct evidence of the fact that we don't live in a homogeneous universe, which is that when you look at the cosmic microwave background, people always tell you that it is absolutely uniform over the sky. Well, actually it is not. If you took a microwave detector and pointed it at the sky, and this was first done way back in the late 70s, actually from a spy plane, from a U-2 aircraft at high altitudes, you find that the sky is in fact hotter in one half and colder in the other half by about 1 part in 1,000. So the temperature of the microwave background is in fact pretty accurately a black body. It's 2.728 degrees Kelvin, but it is slightly hotter here and slightly cooler here. The spectrum is still a black body, it's just shifted by 1 part in 10 to the 3. Okay. And this is about 100 times larger than the little intrinsic fluctuations in the microwave background, which are about 1 part in 100,000. Right? So this dipole that we see is unlikely to be something intrinsic. That is, at least that's what we think. We will have to experimentally test whether that is true. But we think that this is really not intrinsic. It is because we are not stationary with respect to the reference frame where the microwave background is truly isotropic. We are moving with respect to it. So the inferred, so 1 part in 1,000, so delta T by T is 10 to the minus 3. It's also V over C. So actually what you have to do is just a special relativistic transform and ask what does a moving observer with a velocity V see if you are surrounded in an isotropic bath with the temperature of T. And this is an exercise that was first done by Peebles and Wilkinson. In fact, I often set it in my special relativity lectures as a nice exercise to do. And you will see that you will get a dipole pattern, which this exactly is. Okay, 1 plus cos theta pattern. And the magnitude of the temperature decrement or increment is proportional to V over C. If that's 10 to the minus 3, that means we are moving at a velocity which is about 368 kilometers per second. Right? Speed of light is 300,000 kilometers per second. In fact, there is an additional vector towards our local group. So the local group is moving about twice as fast to the microwave background. So the CMB is isotropic only after we do a reverse boost to the frame. We cancel out the velocity, then it will look isotropic. And therefore, it is clear that the universe is not homogeneous locally. This is the evidence. But only on scales larger than some value, we believe that we get to homogeneity, and the universe should look homogeneous from that frame, but we have not yet got to the frame. So the question is, on what scales do we converge to the CMB frame? Yes?
That velocity, 300 kilometers per second.
Yeah.
Is that rotational velocity of?
No, this is just linear velocity. So
rotation of galaxy.
no, not rotation of galaxies. Oh, you mean what is the source of that velocity? No, our entire galaxy is coherently moving at 368. The sun's going around the galaxy at a velocity of around 220 kilometers per second. But our entire galaxy is moving like that. So actually, when I put a microwave detector, I'm in my own frame, right? My frame is doing many things. My frame is going around the sun at 30 kilometers per second. I'm of course spinning on my axis to start with. Then I'm going around the sun. The sun is moving around the galaxy. The galaxy is moving, right? So a lot of little vectors have to be added together. So this observation which is being made in my frame tells me that I'm moving. Right now, I think I'm standing still, but I'm actually moving at 368 kilometers per second. This is the evidence, right? Why I'm moving is the next question. So the answer is that it is not that this is due to my motion around the galaxy. This is actually the coherent motion of the galaxy itself. Because the microwave background should be the same for any observer in the galaxy, right? So earlier I said I can't actually move to somewhere else and make the observation, but in this case I can be pretty definite that the microwave background is not just some show created just for me. It must be the same whatever star I'm on. In fact, it must be the same for any galaxy, right? So I think that's a reasonable assumption. I don't have to appeal to the cosmological principle. So we did an exercise. This was just a few years ago, with Arman Shafilou, who was in fact a student from IUCAA, and a couple of astronomers in Paris. We took the distribution of, so there has been a lot of interest in supernovae. So because of that, the redshifts have been measured, and we have a large sample of supernovae up to a redshift of about 0.1. So we can do tomography. We can take shells in redshift around us and count the number of supernovae in each one, and we find that there is a dipole anisotropy in the supernovae distribution as well, right, in roughly the same direction. So this is the CMB dipole pointing in this direction, and this big red patch with the central, that's the uncertainty. This black point is the supernova dipole anisotropy, right, and they're roughly in the same direction. But because I can do tomography, I can measure this in different redshift ranges, and I find that we are moving at something of order of 250 kilometers per second, not quite the CMB velocity, up to the maximum range I can go in the supernovae, which is a redshift of 0.06, which corresponds to about 260 megaparsecs. So this is the velocity that I'm inferring from the supernovae, but according to the standard cold dark matter model, our random velocity should be decreasing. So there is a discrepancy, there is a significant systematic discrepancy between the velocities that are measured with which we are moving and what we expect from random fluctuations. There will always be random fluctuations. So Andromeda, for example, is not moving away from us, it's falling towards us. Okay? That's an example of a fluctuation from the Hubble flow. And these peculiar velocities will always be there, but this appears to be consistently higher than what you expect from the standard picture of galaxy formation. And another group finds an even larger bulk flow. The uncertainties are very large because these observations are very hard to make, and if you're honest about your systematics, you'll get a large error bar, right? So all this suggests that there is, some room here to question whether the basic model that we are using for cosmology is indeed correct at the level that we want it to be. And in particular, this is quite clear that we haven't got convergence to the microwave background frame, even as far out as the Shapley supercluster, which I'll show you in a second, which is at about 260 megaparsecs. I will often write it as something times 1 over h. Little h is the Hubble parameter in units of 100 kilometers per second per megaparsec, and the observed value in our neighborhood is about 0.7. Okay? So we often put it in those terms just to show that we are not quite sure of the value of h. Now, when we made this observation, there was some concern about whether our statistics was actually enough, because there were not too many supernovae. We were using something called the Union Catalog, which was the current one at the time. So some colleagues who had been involved in a different survey called the Nearby Supernova Factory, they had more data, and they decided to repeat the analysis, and they in fact found the same answer. They found that the interpretation of this velocity is not, as you asked, whether we are going around the galaxy, it's that something is pulling us. There is a huge density and homogeneity in some direction that is pulling us towards it in much the same way that we are pulling Andromeda and it's falling towards us. Okay? So the fact that there is a big lump of matter immediately tells you that the universe is not homogeneous. If it was homogeneous, then every direction should be equivalent. Nothing should be pulling us in one particular direction. And what these guys do is they infer the amount of matter that you need to be giving us the velocity that we are currently moving with, as we determine from the microwave background. And the mass that is required becomes larger and larger as you go further and further, because the gravity is, of course, dropping off as 1 by r square. So you need a bigger mass in order to do this. And the attractor mass, as you see here, is going up to something of the order of few times 10 to the 17 solar mass. So the galaxy's mass is about 2 10 to the 12, including the dark matter. So this is 100,000 galaxies. It must be some huge structure, yeah?
So could it happen that after CMB decoupling, that the universe accelerated in one direction?
Yes.
Would it be that velocity?
Well, there has been a speculation that you could start thinking of, yes, something like a tilted universe, something as weird as that, right? That's a possibility. Right? And in fact, if we can exclude all other obvious reasons, then indeed we'll have to start thinking along those lines, right? But I think before we start thinking of, very weird sort of solutions like that, to convince everybody, you'll have to first show that it is not just some random fluctuation, right? And then we can try to hone in on that. But you're right, we might have to start thinking along those lines. So this paper, this includes, by the way, Saul Perlmutter, this is the supernova cosmology project people doing this nearby supernova factory data. And what they are saying is that even if you go out to something called the Sloan Wall, we only went out as far as Shapley. They have gone out a lot further, and this velocity is continuing. It is not yet died out. Okay, so I'm only addressing here the much simpler question of, are we reaching homogeneity? But in fact, the more we dig, the more we are sort of, bringing up all kinds of weird things. So let me just, summarize this part. This is some new data from the so-called 6-degree field galaxy survey, which is part of that same APM survey that I showed you, peculiar velocity field. And what they're showing you here is the direction of the CMB dipole plus the dipoles inferred by various people, not necessarily the dipole, the streaming velocities that have been inferred by various groups. The measurement that we did, I referred to, is this yellow dot here, and others have done different measurements. As you can see, they're scattered by tens of degrees. These are very uncertain measurements. But what is clear is that if I plot the velocity that is inferred as a function of the scale, this line that you see here, this dotted line, that is the expectation for a standard cold dark matter cosmology with Gaussian random fluctuations, and it is falling off. But the measurements that we have made, and in particular the one that 6-degree field has made, this is not, by the way, published in a journal yet. It's in the bulletin of the Anglo-Australian Telescope. It is definitely significantly higher. Again, it's not that significant. It's only about 2 standard deviations, right? But it is beginning to get interesting and worthy of further investigation. It is higher than what you expect. So in the bottom line from all this is that we have not yet converged to the CMB frame, even though we have gone beyond 100 megaparsecs. This is the bottom line. Okay, that does not mean that there is no convergence. What it means is that we have to think a little bit deeper about the problem. So this is what the sky looks like. These are pictures taken with the infrared telescope, which is not obscured by dust, so it gets a nice view of the sky. And when it looks very locally, you see the Milky Way disk. When you look up to redshift of 0.01, you start seeing the nearby galaxies and their tracery. When you look at the next redshift interval, that gets more and more, that gets more intense, and so on as you keep going up in redshift intervals of 0.01. So, by the way, these are also things you should do in your head. Redshift of 0.01 is small compared to 1. So roughly speaking, the recession velocity is just z times the speed of light, right? So 0.01 times 300,000, that means it's receding at 3,000 kilometers per second. So what is the distance? The Hubble parameter is 70 kilometers per second per megaparsec. So that will go into 3,000. So it's about 40 megaparsecs, right? So you get that is it. So this was a distance of 40 megaparsecs. That's 80 megaparsecs. That is 120 and so on, 160. So you can see how we are going. This formula that I just gave you only works when z is very small compared to 1, right? Because actually it is not a Doppler velocity at all. It is the cosmological redshift effect. So the biggest scales that you have so far probed to with objects like the telescopes that I'm talking about is about the scale of 0.06, okay, which is about 250 megaparsecs, which is a pretty large scale, right? But not so large a scale that you cannot entirely discount fluctuations at the level of 3 sigma or so from a random distribution, which will still give you some structure over there. And indeed, you see structure over there. Okay. Now, it is beginning to look homogeneous, but it is still not quite homogeneous. And we now know from these exercises that you have just done with the streaming velocities of galaxies that we have not yet totally converged to the CMB frame just there. Okay. So I think I'll stop here. I'll stop on this slide, because what we'll do in the next lecture is start constructing a mathematical model of the universe, which actually assumes that it is homogeneous and isotropic on the larger scales. But before I do that, I just wanted to instill a little doubt in your minds about whether that standard thing that we always do is a closed chapter, or indeed that there is little more research to do, because I know that many of you are looking for research problems. So whenever I can, I'll give you examples of things that are things which are worth lifting the rock and looking under. Okay, and this is an example. So I think I'll stop here now and take questions. Thank you.
So questions?
Yeah?
So you mentioned in the beginning that fluctuation density decrease with size.
Yes.
Is that because just of my scale, that scale I've chosen, scale I would choose will be comparable to some magnitude, and as the object of magnitude increases, my uncertainty in my measurement will decrease?
Well, obviously that depends on what the underlying model of the fluctuations that we are using, right? So let me find that plot, and yeah, no, that plot is, what is that plot? Yes.
This is basically the sigma, right?
Yes, this is basically, that's correct.
Sigma
So,
square.
yeah, so what you actually see here is a expectation of the fluctuations as a function of scale in a particular model. So answer the question, you have to tell me what model am I using for the fluctuations. This is the expected level at which the fluctuations will go down if my initial fluctuation spectrum is constant amplitude independent of scale, a so-called scale invariant or Harrison-Zeldovich spectrum with magnitude of order 10 to the minus 5, right? So that's the level that I go to on the very largest scales, right? And this is then going to grow under gravitational instability in the sea of matter that is in the universe at a rate proportional to the scale factor. So it has a certain time to grow from last scattering till today. So in other words, I have to have a whole theory of structure formation to answer what is the expectation for these fluctuations. A priori, I cannot say. I have to have a specific model in mind, right? And this particular model, which is the cyan line there, is the standard model of cosmology, which is, as you can see, is doing a pretty good job, right? The fluctuations are increasing towards small scales, much as you would expect if the fluctuations are growing under gravity. And in fact, one of the things you can infer from that is that the amount of matter that is needed to allow that growth to the present value, right, is about 10 times more than the amount of matter that we see in baryons, and that is precisely the evidence of dark matter that I'll come to in a later lecture. Come on, you must have some questions. Don't be shy. Ask whatever comes into your head. It doesn't have to be clever.
Nothing. By the way, there is a prize at the end if you do ask questions, and if your questions are very stupid, you are going to get a prize.
That's right. I've got a set of all the Nobel lectures, which is the. When did I?
It's with me.
It's with me. Yeah. So that is the prize for the most interesting question. She'll be the judge.
Ask.
So in the beginning, you showed a map of the galaxy number count. It was circular, 2D circular.
Yes. Yes. This one here.
And by the end, with the map which you were seeing, like it was
Yeah. This one. Yeah.
And by the end, with the map which you were seeing, like
It's like oval. Yeah.
How do we map?
Okay, so the oval map is actually a map of the whole sky. Okay, so normally the maps that you are shown, let me find a map that is, okay, I have to go to. So normally the maps that you are shown, like say this one, let's say, this is a map of the whole sky, which is projected onto, I mean, obviously I want to show the whole sky, right? So this is a particular, so the whole sky is a sphere. So I have to map it onto a plane. So obviously there is a singular point, which is the point at which the sphere is touching the plane. And then I have to have some mapping, it's just a function, which takes every point on the sphere onto a corresponding point on the plane, right? that will be unique apart from the singularity where the sphere is touching the plane. But if it is isotropic, then it doesn't matter which point is touching the plane. All points are equivalent on the sphere, right? So that particular mapping, there are many such possible ways of doing that. There is not one unique way. So this is the same ambiguity in the case of the Earth. When you make a map of the Earth, the standard thing that is used is called the Mercator projection. That preserves the directions, but it doesn't preserve the areas. So, you know, Greenland looks huge. It looks bigger than Africa, right? And in reality, that is not so. So you might have seen other projections. There was one called the Peters projection, very popular a few years ago, which tried to show the real areas of things, because most of the area of land on the Earth is actually in, you know, around the tropics. And, you know, there was even a political undertext there as to, like, the Mercator projection actually makes the little countries up towards the pole look much bigger than they actually are, and squashes the huge continents near the equator. So the same ambiguity is there for mapping the sky as for the Earth, right? And but of course it doesn't matter as long as you know what is the maths we are doing. The maths knows exactly what the mapping is, and it can, so visual impressions are not what we go by when we are doing quantitative work. Okay. Nevertheless, visual impressions are good because a lot of the things that we try to do by intuition or trying to see stuff like that. But in general, the rule in astronomy or cosmology is don't trust your eyes. You know, your eyes can pick out structure when there is no structure. So on a map of the cosmic microwave background, people tell me that, let me see if I can have a picture of the cosmic microwave background. Maybe I don't have that particular map, but there is one where you can, if you look on the sky, you can actually see, well, okay, I don't have the real map. The map with the fluctuations, which will come in a later lecture, some people claim they can see the initials of Stephen Hawking on the left-hand side. You know, so your eye can always see patterns on the sky that may or may not be there. But to come back to your question, all these are full sky maps, right? But that particular map of the radio sources that I showed, that is actually a very old map, and that in fact is from the NRAO VLA survey from many years ago. So this is actually showing only the part of the sky. Oh yes, that's important actually. They're only showing the part of the sky that is visible from New Mexico. The full sky is not visible. So ground-based telescopes don't actually see the whole sky. They only see what is delimited by their particular position. So for example, a telescope in the northern hemisphere cannot see the galactic center. That can only be seen if you go to the southern hemisphere. No such problem for a satellite. So when we do full sky maps, we try to do it in satellites, which can point any which way. Or we try to patch together maps made from the northern sky and the southern sky. Right? So this particular map is not very good, and in fact I was not going to discuss it, but very recently we have done some work which is actually very intriguing, and I didn't want to confuse you further. I think a little bit of confusion is good, but maybe this is even more intriguing. So here is a map of radio sources. Okay, so this is the NVSS radio survey, the one that is done from the northern sky, right, which you have patched together with a survey which is done from Molonglo, which is in Australia. So you get a full sky map, and we have taken out all the radio sources which are in our galaxy. That's our galaxy that looks like that. And this is something that was actually first noticed by a astronomer in Ahmedabad, that if I looked at this map of radio sources, I also see a dipole, right? In fact, you have repeated the exercise, and the dipole is because you see both something called an aberration of galaxies, aberration of light, which was first pointed out by Bradley, and you also see a Doppler boosting because of our motion. And what we get from that distribution of radio sources is a perfect cosine function, okay, very good dipole in the data. Now this is, as you might expect, these radio sources are at a redshift of 1. We should see the same dipole in the radio sources as we see in the microwave background. It's even in the same direction, right? But there is a problem. The velocity that we infer from the actual dipole is 3 times bigger than we infer from the CMB, okay? So this is, here is the dipole. You can see it very clearly in the distributed radio sources. Now I have mapped it onto the whole sky. So the things which are on this side are actually a little fainter than the ones which are on this side. So this is aligned with my CMB dipole, right? As to why it is 3 times faster is a big puzzle. We thought it might be because there is some local structure that is biasing the observation. So that's why you took out all these galaxies, and that didn't change the result anyway. It's still 3 times faster. So, which then that would kind of make the kind of thing that you are suggesting earlier even more, weird, except that this fluctuation. So what we can now do is Monte Carlo simulations. We can take a sky which is uniformly covered with radio sources and ask how often by chance would we get a nice little dipole pattern like that with a velocity that is 3 times faster than the CMB. And the answer, surprisingly for me, is that it can happen about 0.7% of the time. Okay?
So it might just be a random.
It might be a random thing, right? So, so this is sort of less than 3 standard deviations. Okay? So it is an anomaly, and if I look at it visually, it looks like an extremely striking anomaly, right? But the only way to be sure that it is a real anomaly and not some fluctuation is to do a Monte Carlo simulation of the same thing with exactly the same cuts, the same choices, the same filters. Everything I'm doing to the data, I do to the Monte Carlo, and then I ask how often do I get that. And according to my postdoc Mohammad Ramiz, it happens, enough of the time that I cannot claim that it is a discovery. The only way to settle the matter would be with the forthcoming square kilometer array radio survey, which will see millions of them. And that will have the statistics to either exclude this as a fluctuation or nail it. So I'm really looking forward to that. And, interestingly, the chap who has just been put in charge of this cosmology survey in South Africa is in fact an ex-student of mine, I just discovered, who is also interested in the question. So we are definitely going to look into this. But I'm just showing you this as a taster for this subject is not closed chapter at all. Okay, there are lots and lots of very important and interesting questions to do with the foundations of cosmology. Right? And I think more people should be looking at these things. Yeah? I'll come to that in the next lecture. I'll show you the data and we'll see what the significance of that is. So again, it's not a matter of questioning things, from an ideological point. It's a matter of, is the data convincing? So I just said, I've discovered this. I would like it to be true, but I have to admit that it's only about 3 sigma evidence, 3 standard deviations, right? What I'll show you is that the evidence for acceleration from supernovae is also less than 3 standard deviations. So then you have to ask yourself, do I believe a 3 sigma result? It could be a fluctuation. It could be true. You can only tell with more data. So last year, for example, this particle physicists here would know there was a fluctuation which went up above 4 sigma. There was a peak in the so-called diphoton peak at 750 GeV at the Large Hadron Collider. People got very excited. I don't know how many papers were written about it, interpreting as a new physics that had been found. It went above 4 sigma, which is a lot more significant than this. And then it disappeared. It was just a statistical fluctuation. Okay. Some years ago, I actually wrote a paper about a particle called the 17 keV neutrino. It was discovered with 7 sigma significance. It went away. It was a systematic issue with the window of the beta decay experiment that was measuring the neutrino mass. So, well, in my own career, I've seen at least 3 results which were more than 5 sigma come and go. 5 sigma is our minimum threshold. Okay, I don't believe anything which is less than 5 sigma. Even 5 sigma is not necessarily sufficient, but typically that is the benchmark. 3 sigma is not worth getting out of bed for.
Sir, something that you mentioned very briefly in answering this question was
self-centered universe.
Yes.
It sounded very fascinating to me. Can you elaborate?
Well, so that's the question is there an intrinsic direction in the universe, right? So, to most intents and purposes, the universe looks pretty isotropic, and that is our received wisdom. It's isotropic. You can do very precision experiments. So people do. So having a preferred axis in the universe would also be a violation of Lorentz invariance. So that is why there is a huge amount of interest also from people doing fundamental physics. They do experiments which are sensitive to a direction. So you might measure the magnetization of something with respect to the Earth's axis, and you do it, over 24 hours when the Earth's axis is moving, and you see if ask if there is a change. If you found a preferred axis in the universe, it would be of fundamental significance. What that significance is the next question. But just finding an axis of any kind would be very significant. So far we have not found anything which is compelling. But there are many indications from different sets of data, and like the one that I'm showing you. Now, what if something like this actually becomes 5 sigma? Then what will you do? Then you have to start asking, if you have discounted all possibilities such as local contamination, systematic bias, whatever, you can ask if the metric of space-time itself that we are using has an intrinsic direction, that it is not so locally we think everything becomes Minkowski space-time. On larger scales, as I will construct in the next lecture, the Minkowski space-time becomes Kerr space-time, but locally it still reduces to Minkowski, no preferred direction. Might we have to take the much more drastic step of having a built-in direction into the metric, okay, which will persist onto, not necessarily persist onto smaller scales, but at least is there on large scales. Okay? So the indication for this has been this indication for large-scale peculiar flows. So there was one more observation which I didn't mention, which is from studies of the X-ray emission of clusters of galaxies by a group led by Kashlinsky at NASA. They claimed a much larger peculiar flow of something like 700-800 kilometers per second, extending out to about few hundred megaparsecs. Okay. That's something which is impossible to generate. If it is true, it is impossible to generate by random fluctuations. It is in a particular direction. So then you sort of ask if the metric of space-time itself, well, that's the term tilted, is tilted in that direction. And that is what is imprinting itself on the observations of galaxies, velocities, dipoles, whatever. But that would be indicative of some initial condition, and most people are very skeptical about that, because if that is there, then why isn't it there in the cosmic microwave background, right? Next, the answer to that is, well, maybe it is there in the cosmic microwave background, which we claim is isotropic, but looked at in much more detail, very recently we are beginning to find that there is a possible dipolar modulation of the fluctuations on the microwave background itself. Okay. One possible cause for that could be just what we're discussing. There are other possible causes.
So suppose the effect of dark energy increases over a period of time.
Yes.
Then after CMB decoupling, the effect of dark energy as distance is increasing between galaxies.
Yes.
Supposedly it is increasing. That would bring us into.
Yes, but normally, if dark energy is normally negligible at the time of microwave background decoupling, because the matter density is going up as the Q of the redshift, so it is 10 to the 9 times bigger then. Okay, 1,000 million times bigger, so it's totally negligible. And we can also directly put a bound on it from the fact that the expansion rate during primordial nucleosynthesis we can match pretty well from observations as due just to radiation. There was no other effect. So that limits any other component to less than few percent of the radiation thing. So we have constraints from both ends, and that tells us empirically that it is very hard for there to be any component. I'm not even questioning the theoretical basis for it. I'm just saying empirically it's very hard to have such a component. Right? I think that it is good to speculate, but you have to speculate with along lines which are consistent with all the empirical constraints, right? And that we have to know. So there is a vast set of such constraints. Actually, in the early universe, there are not that many because we don't have that many observables. And many of these uncertainties are kind of convoluted into the same observable. So therefore, there are a lot of so-called degeneracies. But in principle, one can, separate all these things with enough data. That's the idea. So I think it's a much more constructive way to start thinking, how can I get independent information, say, about the isotropy of the universe at large redshift. All these observations I'm making are at low redshift. The microwave background is at a redshift of 1,000. Do I have any constraint on the isotropy of the universe at a redshift of 10 to the 12 when nucleosynthesis happened? What would have happened? How would the yield of helium have changed, let's say, if there was large anisotropy? Right? And in fact, interestingly enough, these are the questions that were considered by the pioneers, by Charlie Misner and so on. They talked in terms of something called the mixed master universe that he talked about, which had a huge amount of anisotropy. And in the microwave background in particular, a particular pattern was seen a few years ago that looked like a Bianchi universe, which is something with large angular momentum. So the standard assumption is that none of these things are compelling, and that is correct statement. None of them are compelling. But there are lots of interesting indications here and there. And sometimes you find something only when you go looking for it, because it's very subtle. But when you do this analysis, the first thing you realize is that notwithstanding all this talk about precision cosmology, that's just a slogan. In reality, the data is actually very limited. Okay? It is a lot more than we had in Einstein's time when the standard model of cosmology was formulated. But much of this data is not being actually used. People just go past to studying the implications of the same standard theoretical picture that was formulated 70 years ago. So what I'm really trying to get you guys to do is to make use of this data. There's a lot of data. Think up things that can be done with it. Right? New tests, new statistical procedures, asking new questions. It's always good to have some idea in mind. So for example, if you have the idea that there is a tilt to the universe, you can ask, is there some data set that will answer that question, or which I can interrogate with that in mind? So, yeah.
So you mean that it was like there is a difference in the rest of the same chart and
Yes. So right now we think that there is a difference in the rest frame of this microwave background and us, but it's a very simple one. We are in an inertial frame moving at 368 kilometers per second in a particular direction through that one. That is the only difference. And so I can cancel that out easily, right?
and that's why the X-rays results are coming from a particular direction.
Sorry, the what?
You said that there is an excess of these X-ray data that is coming from a particular
Oh, that, yeah. So that is studied by looking at clusters of galaxies and their X-ray emission, and that seems to suggest that there is a large streaming flow, even bigger than the velocity through the microwave background, right? And that at first sight looks ridiculous. How can that be? So this is an example where you actually see, even from our vantage point with well-known objects like radio sources, that there could be a velocity that you infer from the data which is larger than that from the CMB, which makes no sense whatsoever. But that's what the data are telling me, right? So there are only two possibilities. Either I'm misinterpreting the data because there is some systematic bias in how I'm interpreting it, which I don't know about, and we are very much aware of it because we don't want to jump to some crazy idea before removing everything that could have misled me, right? But if it turns out that even with the square kilometer array data, this result stands up, or the Kashlinsky result stands up with a bigger survey of X-ray clusters or whatever, then we have to start seriously thinking about what's happening in cosmology.
Okay, I think we can break for tea
Yeah.
and continue the discussions outside.
Sure.
We'll come back at 11:30.
Thank you.
Let's thank Steve for the
Very good. I think it was more or less in time. So they'll take some time to warm up before they ask questions. Oh, sorry. Yeah. Poonam, shall I switch off the projector? Is somebody going to use it now?
Yeah, Patrick will.
Okay. Well,
Probably you-
but well, I just wanted to know if you switch it off now.
Yogesh, this is
Yeah. No, that doesn't make it off.
yeah.
Hmm? That one. And I just want to switch off this microphone.
I switched it off.
Yeah, but then this buzzing sound will be there because.
This I will put this side.
Huh? Yes, कौन सा sound system off? Actually, I don't need that. वो on क्यों?
साउंड सिस्टम चंदन को बुला ले
हाँ.
चंदन
Thanks.